Hello, everyone. Hi, Quiva.
Okay. Hi, Peter. All right. Thank you to everybody who has joined us again today. As you can see, we have resolved many of our technical issues that arose yesterday. I'd like to welcome you all once again to the lockdown lecture series of the Dublin Institute for Advanced Studies. My name is Kiva and I will act as your moderator today. And I also have the pleasure of introducing our series and speaker. This series came about in response to the COVID-19 pandemic, and it is to help DIAS mark its 80th anniversary in an online format with lectures from our staff. Today's lecture is from Professor Peter Gallagher, who is the Director of Dunsink Observatory and the head of the Astrophysics section at DIAS School of Cosmic Physics. Professor Gallagher leads solar physics and space weather research for the Institute. And so today's lecture is called Exploring the Sun-Earth Connection with ESA's Solar Orbiter. Professor Gallagher recently worked on the ESA Solar Orbiter satellite as a co-investigator for the STIX instrument. And this satellite launched in February 2020 from NASA's Kennedy Space Center in Florida. Over the course of the lecture, we would ask attendees to ensure that their microphone is on mute and that their video is also turned off. Also, please note we will be recording this lecture and it is being streamed live to YouTube at this time. We will collect questions via the chat bar during the lecture, and these will be addressed in sequential order once Peter has completed his talk. Following this, there will also be an opportunity for further questions. So without much further ado, and maybe 24 hours later than originally hoped for, I'll hand you over to Peter Gallagher.
Great, thank you so much, Quiva, and a pleasure to be here with everybody again. Things don't always work out with technology, but we got there, and I'm actually quite happy that this happened because this morning we had a solar flare, and it was our first solar flare in quite a number of years, about 3 years. So this is the whole essence of the research that we do in my research group, and I'll show you some of those data later on in the talk. So it's as if I planned this to go wrong yesterday, but we're all online today, and welcome along to the talk, and looking forward to telling you about the Solar Orbiter spacecraft, which was launched by the European Space Agency and NASA earlier this year. And I'm going to talk about some of the science that it does and how we got there. It's a little bit of a talk really about the journey that we have taken with Solar Orbiter and where Solar Orbiter is going. A little bit about us before I start. The Dublin Institute for Advanced Studies is formed 80 years ago, and one of the largest research groups within DIAS is the Astrophysics Research Group, and here are all the happy people who work in the group. I'm head of that group, and we have people from all around the world. We have people from France and Germany and from the United States, from Ireland, all around the world who come to work on fundamental problems in astrophysics around star formation, looking at planets, and also looking at the sun, which is my group's research area. And we're supported by lots of different bodies, both within Ireland and also within Europe as well. So Science Foundation Ireland, the Department of Education, the European Research Council, ESA, and so on, all support the kind of research that I'm going to talk to you about today. And we do a spectrum of research. We work on ground-based telescopes, such as the two that you can see here. This top one here is in Birr in County Offaly, and this is one that I was involved in building, and it looks at radio waves from exploding stars, from the early universe, and from the sun. Unfortunately, we weren't observing this morning, so we didn't catch that solar flare, but that's okay. There'll be plenty of other opportunities to catch some solar flares maybe early next week. But we also work with large optical telescopes that you have in Chile, this is the European Southern Observatory, and Ireland. It was wonderful that Ireland joined the European Southern Observatory last year, giving Irish scientists access to the largest telescopes on the surface of the Earth. But then you can go on up into space, which is really where many of our observations are taken. One of my colleagues, Professor Tom Ray, is working on the James Webb Space Telescope at the moment, and many other facilities that we're working on. And of course, all the data that comes back down from these has to be understood, and we do that by data analysis, or else we can do it using theoretical models as well. So we use the Irish Centre for High-End Computing's facilities regularly as well. But today I'm going to focus on the sun and talk about its interesting physics. Now, when we think about the sun, this is probably what we think of, a big round ball that looks, you know, like an orange. It has kind of a crackly skin to it. And that surface is about 6,000 degrees Celsius. So it's quite hot there. But if you move into the core of the sun where nuclear fusion is happening, the temperatures can creep up to nearly 15 million degrees Kelvin. And that's where nuclear fusion happens. And it's that energy that really powers the sun. It's what keeps the sun from collapsing in on itself. And it's the ultimate source of energy that keeps the sun shining. Now, the sun isn't always so quiet. From time to time, large solar flares can happen, and they happen in these regions here, which are called sunspots. So you can see my cursor there circling one of these. And this sunspot here is about the size of the Earth. So you get 109 Earths the whole way across the sun. So it's a very large object, and it just shows how small our planet actually is. The sun, of course, isn't always that boring. Sometimes it can be much more exciting, much more energetic. And these are a sequence of images taken by a NASA satellite called the Solar Dynamics Observatory, SDO, over the past 48 hours. So right up until about 8 a.m. Irish time this morning, or 7 UT Universal time this morning. But it just shows you the atmosphere of the sun. And the atmosphere of the sun is this tenuous atmosphere of gas, mainly hydrogen, but there's also helium in there and also some trace elements. And it has a temperature of 2 million degrees Celsius or Kelvin. Doesn't really matter which unit you use, but it's hot. And we still don't understand why the atmosphere of the sun is hot. And that's one of the challenges that Solar Orbiter has, is to try and help us solar physicists understand why the atmosphere of the sun is so hot. I personally I'm interested in things that go pop in the day or the night, and they are called solar flares or solar storms. And here's one happening this morning. So on the top left of the sun, you can see coming around as the sun rotates around this hot region. And in that region, there are explosions going on. And for a solar physicist, I've been stuck with a boring sun for about 5 years, really. And this is an exciting period as the sun picks up and becomes more active and enters this new solar cycle and produces solar flares and solar storms. So we've been preparing for this moment, and we built the LOFAR radio telescope in Burcastle in order to study these. So there's been a lot of work going on. Likewise with Solar Orbiter, it's also up there to understand these eruptions and also the solar corona and also the solar wind. Now, as I mentioned, there was a big solar flare this morning. So what you can see here is this plot taken from a website that we run called solarmonitor.org. You'll see 2 days ago, the sun wasn't doing very much. It was pretty much flatlining. This shows the X-rays from the sun. Then there was a little pop. And then yesterday there was a few more little flares. But then this morning, as I said, around 7 Universal time or 8 Irish time, there was a solar flare, and then there was another one. So there's an active region or a big sunspot group coming around onto the sun, and over the next week, fingers crossed, we're going to get some more activity. And this means that we as solar physicists can then try and understand them. And if we can understand them, we might be able to forecast them. And that's really important for many applications as well. This is what the Earth looked like this morning. I think this was about 6:30 UT or 7:30 Irish time this morning. And it was really what the Earth's upper layers of the atmosphere looks like, the so-called ionosphere. And it was quiet, not much going on. But if a solar flare goes off, it can cause effects on the Earth's ionosphere and can cause problems with communication systems. By 7:30 UT this morning, this is what the Earth's ionosphere was looking like. There was a large area of the Earth's upper atmosphere that was illuminated by X-rays from the sun, from the solar flare, and then it caused some radio blackouts. So for people in that part of the world, so you can see over large areas of Russia, over China, over some of India, and then over the Middle East as well, this would cause communications and some problems with shortwave radio communication, with ham radio as well. So there was some potential impacts this morning, which I wouldn't have been able to tell you about yesterday. These events, when they produce X-rays, they can also produce ejecta as well. So the gas can get heated up near the surface of the sun, and it can sometimes then explode, and it can come streaming out into space. And these sequence of images that you're showing here shows that plasma, the gas, being heated to really high temperatures and then expanding out through the solar system. And what's also interesting about this image is you can see all these streaks all over our cameras, and those streaks, we'll get back to it again, I'll just play it once more. You'll see those streaks are actually caused by protons, which are the nuclei of hydrogen ending up hitting the cameras, and they can cause long-term damage to the cameras on board spacecraft. In this case, it was the SOHO spacecraft that had the cameras impacted. There you go. There's the solar storm, or coronal mass ejection, going out through space and hitting our cameras. And I spent quite a number of years working on this particular sequence of data. Now, the sun also has a general wind that blows, and these images here are just absolutely wonderful. On the right-hand side over here, you have the sun, and on the left-hand side over here, you have Venus, which you might see on the horizon tonight. And then over here is where we are. This is where we live. And this is 149 million kilometers between the surface of the sun and the Earth itself. And there is a wind blowing from the sun, and transients in the wind called coronal mass ejections moving through the solar system, hitting Venus, hitting Earth, and actually going on the way out to the larger planets, to the gas giants. And it produces the aurora borealis on our planet, and it'll produce aurorae on other planets through the solar system as well. Luckily for us, we have a nice magnetic umbrella around our planet. And this is a model that shows the Earth's magnetic field, and it's waving in the solar wind. And we are lucky to have that. If there wasn't that magnetic field around our planet, we wouldn't have a condition that would be suitable for life on that planet. So we're very lucky to have that strong. We call it a magnetic umbrella, and it deflects the solar wind away from us. So we live down here on the surface, and this is this magnetic umbrella here, and the wind comes in from the left and it blows, and this protects us. But sometimes particles from the solar wind can come down and hit the Earth's upper atmosphere and produce the aurora borealis, which is something that we'd like to forecast better. So the physics that we do can help us to try and understand that. Of course, we have satellites that are doing communications and navigation all around our planet. We relay phone signals and TV signals. There are defense satellites up there. There are satellites that are also doing monitoring of weather and of climate. And all of them are vulnerable to this wind from the sun and to solar transients like solar storms. And we depend on these technological systems as part of our everyday lives. Of course, it's not very everyday to be an astronaut, but astronauts, if they are out in space, can have problems. Here is an astronaut. Of course, this Saturday, hopefully SpaceX and NASA will launch a pair of satellites who will then rendezvous with the International Space Station. And they'll be watching solar activity at the moment as well, because it can be dangerous for astronauts. Now, luckily, the solar storm that happened this morning is from a region on the left-hand side of the sun. So those particles will go out on into space. But over the next number of days, the active region will rotate and be pointing towards the Earth. So we'll be keeping an eye on that and making forecasts of it. Of course, there are, as I said, assets in space like satellites. Here's another satellite and another satellite here. And the radiation from the sun can cause effects on the electronics. It can blind the cameras. It can affect the communication systems. And then right down on the surface of the Earth, you can then have other effects. Right down on the surface, you can have charging of our electric power grid that can cause transformers to trip out. Or you can also have currents on gas pipelines as well. And of course, shortwave communications, as I mentioned earlier, can be affected. And it's funny, when I used to give this talk, I would gloss over this and I think, oh, low probability event, but it could have a big impact, and I kind of disregarded it. But in light of the pandemic at the moment that we have with COVID, I'm taking this an awful lot more serious, that it's a low probability event, but the impact on our society could be large. So this kind of work is important to understand the physics, to understand the basic science, to help us make forecasts and then take evasive action in order to protect these kind of assets. Now, in order to monitor the sun and the Earth system, we have a whole flotilla of spacecraft out there monitoring the sun and monitoring our planet. This is one that I grew up on. This is really where I started my whole career 25 years ago. It's the Solar and Heliospheric Observatory. It sits between the sun and the Earth, and it's constantly monitoring the sun. And really it is on its last legs at this point, but it is a sentinel in space that keeps an eye on what's being launched off the sun, very close to my heart. And there are new spacecraft that have been launched. Solar Orbiter, this is Solar Probe, which was launched by NASA. And then also we have Solar Orbiter, which was just launched by NASA and built by the European Space Agency. Then there are spacecraft that are in around the Earth, and they're watching the Earth's magnetic field. They're looking at the aurora borealis, and they're looking at the Earth's upper atmosphere. Of course, I can't forget this spacecraft up here called RESI, which was launched in about 2001, I think it was, when I was also working on this. And this looks at X-rays from solar flares. And that's quite relevant to what I'm going to talk about later on, because the spacecraft instrument that we're working on really builds on what we learned with the RESI spacecraft. And you can use RESI and SOHO and Solar Probe and all these other spacecraft together as one coordinated facility, a giant observatory, all looking at what's happening on the sun and how it impacts us here on planet Earth. Now, this is the spacecraft that I'm going to spend most of this talk talking about. I've been working on this for about 10 years. It was amazing that it was launched in February of this year after many, many delays. These are not simple systems. And I'm going to talk about some really important aspects of it. See this black surface here? This is a heat shield designed and developed by an Irish company called NBio. And I'm also going to talk about some of the scientific instruments that you can see peeking through the front of this spacecraft. So as it flies around, you'll see these little apertures here. These are where the cameras look through: ultraviolet cameras, X-ray cameras, spectrometers. And then you also have these booms here, which can measure the solar wind and radio bursts coming from the sun. It's packed with scientific instruments built by teams all throughout Europe and the United States actually as well. So it's really very much a multinational effort. So we have what are called in situ instruments and also remote sensing instruments. The remote sensing instruments take pictures, and the in situ ones measure or taste the solar wind almost as it goes past. So we have things on booms that measure magnetic fields of the solar wind and of solar storms. We have things that measure energetic particles that are accelerated close to the sun. We have other things that look at wide angle views of the sun. Then over here we have things like STIX. It'll look at X-rays from the sun. The extreme ultraviolet imager take beautiful pictures of the sun, and I hear rumors that it's got some beautiful pictures already taken. They haven't been released yet, but they will be released to the public, and I'm sure a huge big press release from the European Space Agency very soon. And I'll give you a sneak peek of some things later on, once you don't tell anybody on YouTube. The instrument that we're particularly interested in is an instrument called the STIX telescope. So it's the Solar Telescope Imaging X-rays. And it's only about the size of, well, I'll show you a picture in a second what the size of it is. It's about 1 meter long. And it has a camera at the back over here. And then out the front, it has basically a telescope. And it takes images in a very difficult way, actually. It's very challenging to take X-rays. You can't use a conventional telescope because the X-rays just go through the mirrors. So you have to use this indirect imaging technique, like you would use in a CAT scan, really, to take pictures of these solar flares. And it's led by the Swiss, by FHNW, a university and technical university in Switzerland, but there are many other universities and facilities involved. We at DIAS and at Trinity also are involved. We write the software for it, for many aspects of it. And here is the model of it. Here you have here. This is Shane Maloney giving me a dirty look for taking a photograph of him. But Shane is one of our kind of software gurus, and he's also a solar physicist, but he's responsible for writing software that's analyzing the data coming back from the camera on board the telescope. And this is about a 15 million euro instrument, just to give you an idea for cost, and it took about 10 years to build. This is Sam Crooker here. He's the PI, the head honcho for the space for this instrument. I'm not sure if he's praying or pointing there at the moment, but I'm sure that there were a few rain dances and prayers and so on said before this instrument was delivered to solar orbiter, integrated into the spacecraft, and then turned on. And these two gentlemen have been very busy for the past 3 weeks as we've been commissioning the instrument, turning things on and testing it to make sure that it works well. Now, Solar Orbiter isn't a normal spacecraft. It's going to go inside the orbit of Mercury. So it's going to get to about 42 million kilometers away from the sun. And that means that the front of the spacecraft is going to be 500 degrees Celsius. And the back of the spacecraft is going to be minus 130 degrees. So it's going to be very hot on one side and very cold on the other side. And really sensitive electronics inside the spacecraft don't like that. They don't want it to be hot on one side and cold on the other side. That's not the way electronics like to work. So it needed a heat shield in front of it. And this was put out to contract. And an Irish company came up with a very, very interesting way of doing this. I should say, by the way, that 42 million kilometers is about a third of the way. It's about 0.28 of the distance from the sun to the Earth. So it's about a third of the way from the sun to the Earth. So it's hot in there. There's a lot of radiation in there, 13 times the heating that you're going to get for an Earth orbiting spacecraft. So it needs to be protected. And the solar arrays here, where it gets its pointing from, are actually on a boom here that can be rotated. So when you get in close, you can rotate those around. So you're not pointing directly at the sun, you rotate around and you can protect them from the radiation. This is a heat map, and if this doesn't scare you as a spacecraft engineer or scientist, I don't know what will. This is your €1 billion baby sitting back here that you've spent maybe 20 years working on, and this is the heat shield that an Irish company, Enbio, have developed the technology, the surface coating technology to protect. And here they are here. They were a spin-out company, I think, from University College Dublin, and now based in Clonmel, and also working with DCU as well. And I love that the three of them look so happy with a guy with a blowtorch blowing onto this solar black technology. But they're so confident about their technology that it's going to protect them. So I hope nobody's fingers was hurt in that. I doubt it. They look very happy. And they should be, because it's working well at the moment. So we're very proud of the work that they've done. And there's another company, actually an Irish company called Captech, based out in Malahide, and they did some of the software testing for Solar Orbiter, and both are building heritage now with the European Space Agency, and they'll go on to work with other spacecraft and other space agencies, I would hope, in the future. And Ireland has about 30 companies and a growing number of companies who are working with space technologies with the European Space Agency and with other companies around the world, including NASA. To give you an idea for the scale of the spacecraft, here's what it is. It's a supersized washing machine, I guess, is one way of thinking about its size. I think it's beautiful. And it's about 2.5 meters by 2.5 meters by 3 meters. You can see the two engineers at the bottom looking up at it. And really what they're doing here is they're getting ready for testing. Once you integrate all the instruments onto the spacecraft, you then have to test it. You have to vibrationally test it, you have to thermally test it, you have to acoustically test it to make sure when you send it up on a spacecraft, on a rocket that's shaking, that's making a lot of noise, that the instrument won't fall apart. And I've personal experience with this. We were working on a spacecraft called RESI back in 2001, and when we sent it for vibrational testing, the facility, there was a problem with the shaking unit, and it shook it at 10 times what it should be shaking at, and the instrument was damaged, and it set us back by, I think, 16 to 18 months before we got back on time. And these are expensive pieces of hardware, but they need to be tested before you put them on a rocket and send them on up into space. And you know, you have to be nervous about things going up on rockets. It really is a controlled explosion at the bottom of the rocket that then sends these pieces of hardware up into space. And you know, let's be really hopeful that everything works well for any of the astronauts going up over the next number of years, and we will hopefully see an increasing number of astronauts on their way to maybe the moon and maybe even Mars in our lifetime. So fingers crossed that that kind of ambitious kind of exploration of our near space environment happens in our lifetime. Okay, once it was tested in Munich, it was actually built in the UK, I should say, by Airbus. It was then shipped to Germany for testing. It was then put on board this cargo plane. This is a cargo plane that can deliver large pieces of equipment, be they military, be they aerospace, be they space-based pieces of hardware. It was loaded on board and then sent on its way over to the United States, over to Cape Canaveral, to Kennedy Space Center, where it was then taken off. And you know, as part of the team, I was watching this live on the internet, and then when it was on the plane, I followed the plane across the Atlantic, and then when it was handed over to NASA, then to see it landing safely in Kennedy and then being unloaded. But you know, nervous times for the whole team. Here's another shot just to give you an idea of the scale. There's one of the loading people on the plane, just to give you ideas for how large this aircraft is. Once it got to Kennedy, then the first thing that you have to do is put it into its fairing. This is the protective casing that is placed in. Here's the spacecraft in here. Here's some engineers loading it in, and this is the spacecraft fairing where you wrap it all up and make sure that it's locked in, bolted down before it's placed on top of the spacecraft. And here it is being lifted up onto the spacecraft, so you can see the crane here hoisting it up onto the top. Now this is a rocket that's called an Atlas V rocket. It's provided by ULA, the United Launch Alliance, and then they can launch these heavy pieces of hardware at the top of them into space and put them into interplanetary trajectories. So it can give you the delta V, the kick that's required to put it on an interplanetary mission. And they are majestic things. You can't but love looking at these rockets. Here's what the rocket looked like just in the days before it was getting ready to launch. Now we had a couple of delays in it. Weather can affect it. We also had there could be technical problems, and so there was a number of delays. So there were some nervous times for us. And here's me 5 hours before launch, looking extremely, I was meant to be looking happy here, but I clearly didn't look happy. I looked like a very nervous man waiting for the birth of my first child, or the launch, actually the first launch that I was going to see. And this was on the 10th of February earlier this year. And myself and Shane Maloney went over to meet the Solar Orbiter team and the STIX team to be there for the launch. And it was a nighttime launch, which is a great time to see it. And we got into a VIP section at Kennedy with the rest of the team and sat there. And, you know, people were kind of chatting away quietly, watching Twitter, watching social media for what's going on, keeping an eye on NASA and ESA's social media channels. I got solar on the mind, I'm afraid. So T-minus 10 minutes. I pick up my iPhone. This is my iPhone.
2, 1.
And in the distance, right down on the horizon, just below the moon, you can see ignition. And there she goes.
Another 10 seconds before we get the sound.
And then you get this sonic boom that hits you in the chest. You can see the clouds being lit up now by the 5
seconds. Stand by.
By the burning of the fuel. And then up top, you can see the moon. It couldn't have been positioned more perfectly. I won't claim to have anything to do about that. And these were nervous times as the spacecraft is being launched, as the rocket's being launched with our solar orbiter on board. But as it went up, it began to slow down. And I was kind of looking around. Are people watching this? You can hear the rumble. It's slowing down. I'm thinking, why is this slowing down? And then it begins to move away from us. And then I'm getting really nervous. I'm thinking to myself, hold on a second. And it dawns on me, hold on. the Earth is round, and this is going on a trajectory up, and it looks like it's going down, but that, and you can see the trail behind it. So the laws of physics are working. The Earth is round, and it was inserted into a trajectory
right now
on its way to well, not a rendezvous, a flyby with Venus, and it's still on its way there. Once away from the planet Earth, and it's very quick to get over. You're talking about 20 minutes to get into a trajectory off the planet of the Earth, or outside the Earth's atmosphere, let's put it that way. The first thing it does is start flexing its arms, is the way it looks like to me, but this is its solar panels being deployed, and it turns on its solar panels, or it opens up its solar panels in a two-step motion. And you can see some thrusters firing there as well. The thrusters are positioning so it's facing in the right direction towards the sun. And then the next thing to happen is some of the communications antennas and the booms are deployed, and you'll see that now. So here's some of the booms being deployed. These are some of the scientific instruments, the remote sensing instruments. You'll see another boom opening up here. These are one shot. This is their spring-loaded one shot. And then on those are the instruments. And it was amazing, actually. Soon afterward, we had a launch party, and I saw some scientists sitting around from Imperial College Dublin, sitting around a laptop intently. I wasn't really sure what they were doing, but they saw the first data at the launch party, and they were very happy to see that coming in. Okay, so once that happens, then the next step is to send the spacecraft off on a trajectory through the solar system. And what you're going to see here is launch in February 2020. Here's the spacecraft. It then goes into an orbit, and it's going to, at the end of the year, have a flyby with Venus, and that causes it to move into a trajectory inside the inner solar system. It'll then have another swing by of Venus in August of 2021. And then with the Earth, and that'll bring it into a nice tight orbit. This is when we first begin to do our science. So our real science phases is still another couple of years away. And the reason that is primary science is because we're close. We'll be close to the sun at that point. But over the past number of weeks, we have turned on some of the instruments, and every single instrument is turning on and taking data. Now, there are some bits and pieces of trouble, but everything has turned on and everything is working as it should be. And ESA will do a press release showing some of those spectacular images very soon. So I'm really looking forward to seeing that. Even I, as a team member, haven't seen all of those images just yet. So it's very precious data. The scientists want to make sure that it's going to be the most beautiful picture. So they're working on it at the moment. I should also say, and I should have said this earlier, that Solar Orbiter will fly out of the plane of the planets. So most spacecraft fly in a plane called the ecliptic plane that all the planets orbit in. But as Solar Orbiter does these flybys of Venus and Mercury, Venus and Earth, it gets out of the plane of the planets, and this gives us a view of the sun's poles. And this is the first time we will have ever taken images of the sun's poles. And that's what makes Solar Orbiter really, really quite unique. It'll tell us about what's happening on the poles. You know, and when you see the poles, you'll see its magnetic field. You'll see small bright points. It'll tell us about the corona near the poles, and it'll tell us all about the atmosphere above the poles as well. And if we understand the cycle, it'll tell us about the sunspot cycle and help us do forecasting, longer term forecasting of solar activity. Now I'm going to show you some really interesting data. This, to me, is really interesting data. This is data that came from one of our instruments that we're involved in. And these are counts. It basically is saying, hello, I'm alive. I'm seeing X-rays from the sun. And these were data taken in the past number of weeks. And this is basically spacecraft health data and spacecraft scientific data saying we're seeing the sun. The sun also produced a couple of small little flares over the past number of weeks. Here's the 18th of May, and here's an active region on the 18th of May. This is an X-ray image taken by the Hinode spacecraft, a Japanese spacecraft. But we saw a tiny, tiny, tiny little solar flare. This is with a NOAA spacecraft called GOES. But our instrument saw X-rays coming from this solar flare. So we know it works, and we know it can see the smallest flares possible. So this really is top secret data that I'm showing you at the moment, and there'll be more information about that in the coming weeks. This is also a set of observations of the Crab Nebula taken from this weekend. This is the Crab. It was named by the 3rd Earl of Ross, appropriately here in Ireland. He saw it with the Great Leviathan telescope down in Burcastle. But these are contemporary images, or these are modern images of the Crab Nebula. You can see it's this wispy object, but in the very core of it, there is a bright source of X-rays and of gamma rays from very energetic phenomena happening in it. And this is the dust around it. But you can also see X-rays with our instrument on RESI. Sorry, not on RESI, on STIX, on Solar Orbiter. And when the Crab Nebula, here it is here, went behind the sun, fortuitously, we could see the X-rays coming from the Crab going down and then coming back up here. These two lines here are once it's inside our field of view. And then these two vertical red lines here are when you see, or when the Crab goes behind the sun. So it's basically an eclipse of the Crab. But when you have a great spacecraft out there in space, also there are serendipitous things that happened. And a scientist from Mullard Space Science Lab, which is part of the University College London in the United Kingdom, he spotted that, hold on a second, you're going to go through the tail of a comet called Atlas. And this is Atlas over here. Actually, its nucleus, the center of the comet, began fragmenting, and the Hubble Space Telescope saw this. But it has an enormous tail that trails through the solar system. And this is its orbit here. Sorry, this blue line here is the orbit of Atlas here, coming through the ecliptic plane of the planets. And Solar Orbiter, just by chance, is going to pass through it in the next number of weeks. And as it passes through in the next number of weeks, Solar Orbiter is going to have its instruments on, sampling the ion tail. So there are ions, or the plasma tail of the comet. It may even see some dust in there that pass through the dust tail as well. So that'll be really interesting science that's going to happen in the next number, actually next week and the week after, so the first few weeks of June. So it just shows you, when you have a spacecraft up in space, there are some serendipitous events that can happen to produce some interesting science. So that's the excitement of the launch, the turn on of the instruments, and now we begin thinking and planning for the science that we're going to do once we get inside the orbit of Mercury in the next number of years. And Solar Orbiter really is going to do groundbreaking science. It is going to tell us about the magnetic field. It's going to measure magnetic fields at the surface of the sun and in interplanetary space. It's going to get a view of the polar regions of the sun and tell us about the polar regions. It's going to tell us about the magnetic heartbeat of the sun, the magnetic cycle. It's going to tell us about the wind from the sun and transients from the wind. It's going to tell us where these things happen, when these things happen, how energetic they are. And finally, it's going to tell us about space weather, the weather here on Earth, and how that weather on Earth, or the space weather on Earth, is going to affect the technology that we depend on for our everyday life. And it's not going to do it alone, as I said earlier. There's going to be ESA's Solar Orbiter. There's also another wonderful spacecraft called Solar Probe. Here's Solar Probe here, and it's actually even closer to the sun, but it doesn't have any imagers that are looking directly at the sun. It has an imager that looks away from the sun, and it'll see these transients moving away from the sun, but it'll be nice and close to the sun. We'll be far away from, not far away, but we'll be near Mercury, or just inside the orbit of Mercury. And together they'll coordinate their observations, seeing phenomena happening on the sun, moving through the inner solar system on their way towards the Earth and the planets. And it'll give us a real new view of how the sun works and how the sun affects us on planet Earth and also the entire solar system. Thank you very much. I'm so lucky to be working on this topic. at the moment. I'm clearly very excited about it. And I think we're really entering a golden era for heliophysics over the next decade. So please do keep an eye on ESA's Twitter page, actually on NASA's webpage, on ESA's webpage, and also myself. I'm prone to tweeting a lot about the sun, and with all the activity happening at the moment, I'll be tweeting lots about it. So please do keep in contact, and I'm happy to take any questions. So thank you very much.
Great, thanks a million, Peter. I actually have a question, which
Go
is
ahead.
unusual in these situations. But being somebody who, for instance, has gone to Iceland to catch the aurora borealis and unfortunately totally missed them, didn't see them at all, is there any way to predict it at all?
Yes.
Presently?
Absolutely, absolutely. So with this active region coming around the sun right now, there's an increased probability for the aurora over the weekend. So I would be actually not over the weekend, over the next week, if this active region is active as we expect. So I would expect some aurora borealis and aurora australis over the next week or so. So yeah, definitely keep an eye. It's not good for us. Actually, it's not good for seeing the aurora because it's summertime and the evenings are very bright as you go north. So, you know, fingers crossed when the winter comes, the skies get dark and there's a little bit more activity. But over the next 5 years, in 5 years' time, we're going to get lots of solar storms and really a lot of chance to see the aurora borealis. And, you know, keep an eye on those Twitter handles because there will be forecasts going out about the aurora.
Great, thanks a million. I don't seem to have, let me just double check here. Okay, so we have a question from Matt, and he is wondering how difficult was it to figure out a relatively stable long-term orbit for the solar orbiter, especially one that tilts into a non-planetary plane?
Yeah. I mean, that is the stuff that these orbital dynamicists work on. That's their lifeblood, and they run these, you know, at first approximation Newton's laws, but it's much more than that. And they have ESA has a whole division that works on these kind of models that takes into account the gravity of the sun and the gravity of the planets and the position of the planets. So large numerical calculations are used to do that in order to work out those orbits, and they can do it to great precision, which I find mind-blowing. You know, tonight you'll see, I'm not sure if you'll see Venus tonight. It might be just on the horizon, but you know, to look out at Venus, I've been looking at it the past number of nights. When the sun sets, Venus is just behind the setting sun. To think that there is a spacecraft on its way there, and when it gets to Venus, it'll then swing a left, I like to say, at Venus. And if it's too close to Venus, it'll crash into Venus. And if it's too far from Venus, it'll just go off into the solar system. So there is a little bit of work that the spacecraft can do to try and bring it back in line so that the orbital mechanics work properly. But they are pretty accurate, and I just find it pretty mind-blowing to see how accurate they can do it.
Great. We have a question from Leo Enright there. He was wondering, will Team Ireland be involved in the Comet Atlas campaign? What do you hope to measure, and is getting the way of the instrument commissioning process? Is it getting in the way? Sorry.
Yeah, that's interesting. The suggestion was only made very recently, and almost all of the instruments have been turned on at this stage and tested. STIX, the instrument that we work on, is one of the last instruments to be tested. So I think people are quite happy with the amount of time that they've had. Nobody in Ireland that I'm aware of is working on the data from Atlas. We'll be watching. The STIX instrument will be on at the time, so who knows? We may see particle hits. We may see differences in intensity. So who knows? Again, it's that serendipitous science. But we as solar physicists, of course, will be interested in getting that comet tail out of the way and then getting back on sun as soon as possible. But pretty amazing stuff.
Great. Our next question is from Paul Carberry. He says, thank you very much for the talk. You said early in the lecture that we could or might take evasive action protect our telecommunications if we knew about solar flares. What exactly is the evasive action that you would have in mind?
Yeah, there's a number of ways of doing things. You know, one thing is you can be aware of it is number one. And so you know, say if you're reliant on GPS and you want to do, say, drill an oil well, and you need to use your drill bit has to have it has to use GPS. Well, maybe you just mightn't drill during that period. If you're doing mapping or military operations and you're using GPS, or you rely on GPS, then maybe you won't do it at that time. So that's another way of dealing with it. You can also turn a spacecraft. So if you're facing towards the sun, I have a model here with me. It just happens to be one from Star Wars, but you know, the last thing you want to be doing is looking at the sun like that. So you can minimize your cross section like this. Thank you to my son Fionn for building this at Lego. But you can minimize your cross sectional area, and that's another way of doing it. And you can turn things off if you need to. So there's lots of different things that spacecraft engineers can do, but you are also vulnerable, and you can lose and have permanently damaged spacecraft.
Okay, thanks. Moving on to Paul Evans. He thanks you for your talk, and he is asking, how long do you reckon the craft will keep sending good data?
Wrong person to ask, because I'm a scientist and I'll say I want it on as long as possible. You have to ask the funding gods for the answer to that one. I mean, realistically, there's not joking aside, there is a 7-year mission. We probably will get to 10 years and probably go on longer than that. I think what happens is, when you see a spacecraft delivering world-class science, it makes no sense to turn them off. But what you will do is gradually ramp them down and then begin ramping up new spacecraft, because in 20 years' time, there are younger scientists coming up who are having new ideas, and you want those ideas to bubble through and let those older spacecraft move aside. But hopefully we get a good 10 years out of it.
Great. Jeff was wondering, it's more of a personal question, what got you interested in studying the sun? And was there a moment that clicked, or was it more of a slowly growing interest?
Yeah, very interesting question. I guess I grew up wanting to be an engineer or a scientist. It was just what I wanted to do, and I don't know why. The TV sets back then, had screws at the back of them, and I loved nothing better than taking TV sets apart and having a look at what's in the back of them and trying to understand it. And then when early computers came along, I got a ZX Spectrum and learned to program in BASIC. So it's kind of just always interested in the way things work, and that extended to technology, but also to the way the world worked, and the way the stars worked, and the way galaxies worked, and the way the universe worked. But I guess what got me about the sun was you can fly spacecraft out there and get good pictures of it, and you can even fly through the atmosphere of it. So as a kind of a hands-on practical person who, I call myself an experimental physicist, I liked the fact that with the sun, we could actually get up close and personal with it and fly through its atmosphere. So that to me was very attractive. So, my long-term career ambition would be to build an instrument that goes on a spacecraft. I'd love to do that. I think that's the next thing for my career. But I wasn't born wanting to be a solar physicist, actually. And maybe I'll say that I'm sure my primary school teachers are surprised that I ended up being an astrophysicist, because I really didn't concentrate very well in school and messed around an awful lot, and was much happier out with a gang of other kids building things and building huts and so on. But eventually I got good at maths, and eventually I got good at science. And I think the longer I stayed at college, the better I got, which is weird, but that's what happened.
We actually have a question here from the YouTube stream, and it asks, you mentioned a sunspot is about the size of the Earth. How is the climatic effect of sunspots monitored?
Where is that question?
It's on YouTube, right. So you won't see it there.
Oh yeah, would you read that out again?
You mentioned a sunspot is about the size of the Earth. How is the climatic effect of sunspots monitored?
Yeah, I mean, the sunspots wax and wane over an 11-year cycle, roughly an 11-year cycle. But the total brightness of the sun, which we call its luminosity, only changes by 1/10%. So its climatic effect on the Earth is very small over timescales of decades. If you look at hundreds of years and thousands of years, that is a different story, and the solar luminosity can change. During periods where it's very inactive and very dim, you would expect there to be no sunspots, very few bright points on the sun, and the luminosity would drop. But the sunspots in themselves, even if it is very active, the fraction of area occupied by sunspots isn't that large by comparison with the area of the sun. But on millennia, it's much more of an important aspect.
Great. Well, thanks to Tony for that. And lastly, for the moment anyway, David Moore is concerned that it looks like the communications antenna is not shielded. Won't it melt?
Geez, forgot that one. How are we going to? Well, I'd go up and paint it, actually, if they were looking for somebody to go and paint. No, in all seriousness, some of the booms and the antennas that are out the solar wind are coated. The back of the communications antenna it's actually on a boom, and it deploys down like this, and then the high gain antenna is behind it. But the back of the high gain antenna facing the sun is coated. But if the spacecraft tumbled, we lost control of it, then you would have a problem. But these are the risks that you take with a challenging space mission like that, and that's what makes it all the more exciting as you go and explore, the solar system.
Great, thanks for that, Peter. I don't think there are many more questions coming in. We'll give spoke too soon. Ben McKeown. He says, a fantastic talk, Peter. Thanks a million. Following on from Paul Evans' question, once the spacecraft has finished its useful life, are there any plans to deorbit the spacecraft? It looks like it flies. Okay, I'll let you take it up there.
Oh, sorry, I can see that. I'm sorry for cutting across you there. Yeah, that's an interesting one, and not one I want to think about. I think it's likely. There are a number of scenarios. One of them being considered is to plunge it into Venus. And if you did plunge it into Venus, it'd be an interesting experiment. You could train telescopes on Venus and see what happens as the spacecraft plunges in, and maybe there'd be a plume of material that comes out of Venus. The Cassini spacecraft, which I found very sad, plunged into Saturn. Juno is a NASA mission that'll go to Jupiter, and it probably will end its lifetime by plunging into Jupiter. Will it go into the sun? It's hard to get in there, take a long time, but Venus is probably the most likely outcome, but not decided. And I think the Director of Science at ESA and his advisory committee will make a decision on that. But we don't have to do that for many years.
Okay. Right, we might just give it another minute in case any more questions come through. While we're waiting there, I just want to advise you all of our next lockdown lecture that will take place on the 4th of June. And it is from our School of Theoretical Physics by Dr. Samuel Kovacic. And his topic will be, can we get into extra dimensions? It will be at 1 o'clock again, and registrations will once again be taken via Eventbrite. I am going to just place the link here for everybody now if you want to go and reserve your place. I don't see any new messages there. Peter, did you get any direct to yourself, or?
No, I think that's it.
Great. Well, thank you all very much for attending today, both via Zoom and on YouTube. I will post the link for the new talk into YouTube now once we close down this particular session. If you have any further questions, you can put them to communications@dias.ie. So thank you very much to Peter for his fantastic talk. Yeah, that's all I have to say. Do you have anything you'd like to close with, Peter?
No, thank you very much, and keep looking up and keep an eye on those Twitter handles to see all the exciting stuff happening.
Yeah, I believe we can see the ISS. Is it tonight? It was last night and tonight, is that right?
Oh yes, yeah, it was. Well, yeah. If you look at it, should be around. Oh God, is it? I should know this. It's about 10 p.m. tonight, I think. But go and look it up, and it's in between the moon and the horizon. But you better go and have a look at NASA has a website for it to get the exact times. But yeah, it can be seen most nights at the moment.
Great. Okay, well, thanks again. And I am going to leave the room open for another 10 minutes or so. Peter, you're welcome to stay should you wish, but we do have another meeting starting at 2:15. So thank you very much again and have a great week.
Thank you.